recorded it. Go to the website, to the screen. Okay, last time we talked about the first topic, right? We got air resistance, terminal velocity, and how to calculate them. Shall we start the levels, right?
Yeah.
Levels, yeah. And then spring, okay? We can talk about level spring today, hook snow. Any question before we go?
No.
Okay, have you studied these two topics before?
No.
Not yet, okay. Right, let's talk about level. Go to the screen. Wait a moment. Yeah, I think the simplest scenario would be seesaw. Do you know seesaw?
No.
Seesaw. Oh, Chinese is every kid plays this seesaw. So you see the seesaw. Can you draw this one? Okay, the seesaw. You know, for kids.
Oh yeah, 跷跷板.
Yeah, 跷跷板, 跷跷板.
Yeah.
Okay, see. So this is a simplified one. Okay, the simplified one. And you see, when we start the level, we have to consider the size, all right? But yes, and last time we'll only talk about the mass. We'll talk point mass, right?
Yes.
Point mass model. That was we did last time, right? But this time we cannot treat object as point anymore. We have to count the size. This is called a rigid body. It's part of rigid body. Just the name for this model we used. Because in real world, this being could be elastic, right? But for rigid body, we assume that they cannot change. They cannot change the shape, change the length. All right.
Yes.
So that is ideal case. So in this case, and this point as a thing, so there in other, if this is balanced, and they will be keep. If you put the middle point, can you see? If the both sides are the same, they're balanced. However, if you put the different weight at different position, and do you think they'll be balanced?
No.
Yeah, like this. If these two mass are the same.
Yeah. It's balanced.
It's balanced. And why it is balanced, and then we can work out the force acting on this. In this case, can we simplify this seesaw as just one straight line? So in this case, and we know that this is where it's called axis of rotation. So there are two possibilities. One is go this way, another is go different way. Can you see?
Yes.
Depending on the condition given. And we also choose this position as 0 as origin. Okay. Now these 2 points here, can you see the P and the Q, can be simplified as this position, can you see P and the Q, right?
Yes.
And how do we? And then we'll introduce idea of called arm length. The length from the origin to this is called. Can we call this? Can we use a vector? So this is we use this vector to determine the position of this P, right?
Yes.
And we use a different color to represent this Q, right? So you can imagine if we can consider these two as a vector, can you call it R1? It's R2, right?
Yeah.
And the two vectors. Now we will consider the force acting on these 2 points. Can you work out the force acting on this beam, not the object itself?
On the object or on
on the beam, on the timber. Yeah.
Is it just weight force and normal force?
Yeah. Usual? It's just weight. In this case, we consider another simplification. In this case, this have no weight. Can you see? This beam has no weight.
Oh, then it doesn't have gravitational force because it has no weight.
That's right. So in this case, we only consider the force from acting by this it's normal directional force. You
Yes.
see? So
Uh-huh.
can we draw these two force here? So one, all the downward, can you see? Probably will change the color. So this is force downward. There's another force downward here. Can you see?
Yes.
And in this case, this force, because they are we can argue that. So this is last time we were talking about the force acting on the point mass, right? So if you consider this point mass here, and the force acting on these two objects is this. Let's just do a diagram. So this is just the force, gravity, right? And also normal directional force. Can you see? That is talking. Yes. I'm talking about the two objects. And because they are not moving, so we can argue that these two forces, mg, are equal because they're not moving. Okay, so therefore, we can argue that n take mg were equal to 0, or n were equal to mg. Now, this m is actually the normal directional force from this beam, right?
Yes.
But this force is just this force is a reaction of this normal force. Does that make sense?
Yes.
So that also should be mg, can you see?
Yeah.
So this is mg, it happens to be the normal directional force acting on another smaller object. Okay.
So for this, is it called seesaw? Seesaw.
It's a seesaw, yeah. Seesaw.
Yeah. So this weight force of seesaw is caused by the normal force on the beam.
Yes, in this example.
The relation.
In example. Yeah. Alternatively, we just argue that we just use this diagram for time being. So I just introduced this idea how to determine a quantity is called the momentum of the force, or actually is they write it down here. They call the momentum of force, but actually it's just the torque. One moment. Have you heard of torque?
No.
In Chinese, that's called Ju. Okay, it's called force.
Yeah.
It's called just called torque.
Okay.
So force torque is related to the force by, can we use a tau?
Yes.
We connected it with tau, just T for tau, and then that is just equal to, because the vector is also the vector. If I use this notation, can you follow me? Do you know this cross product between the two vectors?
Where is F?
When we start vectors, right?
Yeah, where is F?
F in this case, this can called F1. This F2. Okay. So the force is acting on a particular point, and the r is a distance from is vector, distance vector, position vector from the origin.
Yes.
And if you know that in vectors we have say this is called the dot product. Do you know the dot product?
Yes.
That can be simply written as a scalar. That's A multiplied B times cosine theta, right? There's also another type of product that's called the cross product. A cross product B.
Yeah.
That became another vector. Can you see?
Yes.
The vector, the amplitude of another vector is called the amplitude, right? It can be written as this formula. Yeah, if you haven't studied that, it doesn't matter. We can, so that equal to A, B multiplied sine theta. So this is called the dot product. It's called the cross product.
Yeah, I've learned that.
You learned that before?
Yes.
So if I draw the diagrams, if I draw the diagram, you can see if this is A, and this is another vector B, right? So can you work out the direction of the C?
No, I can't picture that.
Ah,
but I'm not sure what's the meaning of the product.
Yeah. So this definition. So by definition, the dot the cross product. You can use the right hand. You can use the right hand. Can you see? You can use the forefinger along the, say, in this case, can we call this?
Yeah, I got it.
You got it? Okay,
I just realized, it's a normal of the plane.
Yeah, normal, normal to that plane, normal to this. You can imagine this plane.
Yes.
It's normal to this plane.
Mm-hmm.
Okay, so this is a C. Okay.
Yeah.
And it's you are right. So this is normal. Yes. So that is called the cross product. Okay. So this is called the cross product of two vector. And this is an example. We can apply this cross product idea to represent the torque. Okay. So you can use the right hand to determine the product. You use forefinger toward direction of the first vector and burn it to 90 degrees. Okay. And the sum will give you direction of the product called C. And this called right hand rule is very useful. When you study the magnetic force, you can also use the right hand rule.
Sorry, can you repeat it? Which direction is the perspective?
So for example, I can draw the pictures, and if you assume you put the four fingers, you put the four fingers toward the first vector, is A, right? And then you burn, of course, this time I'm right already, see? Then you burn 90 degrees of your forefinger, and the sum will be direction of this, the sum will be the direction of the C. I got the, I show you how to go to this, I just told this one. I got, for example, there are two vectors, right?
Yes.
And the red one is the first one.
Yeah.
So the cross product, they don't have to be 90 degrees. They could be just less than 90 degrees or larger than 90 degrees. For example, like this one, so 45 degrees. To find the direction of the product, a cross product, what you do, you use the forefinger toward the direction of the first vector.
Yeah.
And burn toward the second vector.
Yeah.
You see, and the sum will be the direction of this product. Does that make sense? So in this case, the product will be like this.
Yes.
Make sense?
So
this is very useful, right? We can repeatedly use this right hand rule to determine the direction of the product.
Yeah.
Let me just go there. So this is a new idea about not the force but the torque. Okay, that is you just and also we know that if you just consider their amplitude, that torque will simply equal to R multiply F and multiply sine theta. So theta is the angle between the two vectors. You see? Yes. Okay. If I apply this formula here, can we work out the torque? Can this torque at the Q? Can we work out the torque here? What is the angle between the two vectors in this case?
But the vectors doesn't start from the same point.
Yes, you can shift. Yeah, you can always shift that. In this case,
right.
you can do translation. You can just we just put this.
I got it.
You got it. So you can translate it to here. Can you see?
Yes.
Okay. So that is R2, right? It's also R2. So what is the angle between R2 and F1?
90 degrees.
90 degrees. What is sine 90 degrees?
It's +1.
+1 is just RF. Do you agree? So when theta equal to 90 degrees or half pi, how about theta equal to 0? What is the sine 0 degree?
0. So
therefore, the torque will be 0.
Yes.
Does that make sense? So when the angle is 90 degrees, and that torque reach its maximum. If the angle is 0, for example, if we put the force, additional force here, Oh, before we go, can we assume this is balanced? All right.
Yeah.
So this is this. I will make assumption. This is a balanced seesaw. Balanced. Sorry. Okay. Seesaw. Okay, so it's balanced, which we assume is balanced. So in this case, if I just take, for example, if the force is toward this direction, can you see that? If we added another force toward the direction of R1, do you think this what is the torque of this additional force? This time, what is angle? Can you see this additional force here?
Yes.
So you just follow this idea. If the angle is 0, what conclusion can we draw?
The torque is 0.
It's 0. Okay, it's 0. In other words, we can argue that if you put additional force, but the angle is a parallel force, and it will not change the balance.
I don't quite get the torque concept. Is it a force?
Torque is not the force. It's related to the force. Torque equal to R cross product force.
Yes, but how is R a force?
I will just introduce a balance condition. Okay.
Okay.
Before we go, how can we describe this balance? Well, in order to make it balance, the torque one must be equal to torque 2. That is a balance condition.
So in this case, the torque is coming towards us, right?
In this case, that's right. The R, no, into the page. At this moment, the F1 is into the page. The torque is into the page. Because these are R2. Do you agree?
Yes.
So if you use right 4 fingers toward the direction R2 and burn into the direction of the force 1, and the sum will give a direction into the page.
So you do this.
So if I just draw the 3D diagram, probably that will help you. For example, in this case, if I just draw a 3D diagram, for example, let's say, if I just do a 3D diagram here, okay, is a seesaw, and yes. They can rotate about this axis, okay. So in this case, F1 is downward. F1 is downward, all right.
Yes.
And R2, if I use the same color, the R2 is from this side. This is R2, all right.
Yeah.
Or we can also call this R2. You see?
Yeah.
So in this way, the angle between these two is this angle. Can you see?
Yes.
So this is R2, this is F1, right? Okay. Yeah, but I probably make too complicated. Can we call it F2? This is F1, all right?
Yeah,
this makes consistent. This is F1, F2, all right? So in this case, the torque will be in the direction. The torque will be direction into the page. Can you see? That will be the torque 1, torque 2. Can you see?
Why?
This is 3D. Can you see this 3D diagram? This 90 degree.
How do you apply the right-hand rule in this situation?
The right-hand rule is that you put 4 fingers. Can you see? You put the 4 fingers. Just assume we just put the 4 fingers this time. The 4 fingers will be in that direction. Can you see? These 4 fingers towards that direction. All right.
So do you like assume one of the force as the first force?
One of the force is what?
Is the first force because you say the 4th finger. Oh, okay.
No. First vector. No, this is first vector.
Oh, okay.
This second vector. This first. This first. This second vector. We just follow this order, right? Follow this order. So therefore, the first vector is R2, the position, and the second vector is force. Okay. So the torque will be toward that direction.
Yeah.
Okay. Now, on the other hand, how about the other side? You can try this time. So this time, the F1 is downward. Can you see the F1 is downward, and the position vector in this case, position vector, just from this one, okay. I just translated that to that direction. You can easily to use that. Can that's R1, you see R1.
Yeah.
Can you work out the direction of poke in this case?
So it goes like
you go forefinger go to the R1, the green one, and you burn to the direction of force one.
Yeah. So it's
opposite. Okay, it's out of page. Can you see? In this case, this will be out of page. Can you see that? Yeah, at the beginning it's a little bit challenging. Doesn't matter. Today we're not go to that far. We just work out this equation to describe the balance condition. All right.
Yeah.
So in this case, if we just, because in our case both theta is 90 degrees, so we can argue that this is equal to, this is simple case. Say R1 multiply F1 should equal to R2 multiply F2. That is a simple equation, can you see?
So it's a multiply of the magnitude, but not vector.
In this case, at this moment is vector. So this equation is a vector. But this is a scalar equation. This is scalar now.
Okay.
I think we'll go to very simple example that we'll consider if this is also balanced seesaw, but obviously the force, I just draw the force without draw the object, otherwise get confused. If I draw the force, two force like this, so this is this is force 1, and this is force 2. Let's put it this side. Okay, so one force is stronger than others, right?
Yes.
This is F1, so this is F1, so this is F2. Okay. Now, in order to keep the balance, just consider this example. All right. If this R1, so this R1, so this distance R1. So given if R1 is equal to, say, equal to 1 meters, all right?
Yeah.
And R2 is equal to, say, 1.5 meters, okay? And if F1 is equal to, say, 15 newtons, and if this balanced, what would the question? What would be the F2? Can you solve this problem?
F2 would be 50 over 1.5.
Can you write here? Can you write down? Yeah. So this distance will be, this would be 1.5, and this sorry, this is 1. Sorry, this is 1. This is 1 meters, and this would be 1.5 meter. Yes. Yeah. You have calculator? You got a calculator.
I can do it by heart.
Oh, good.
It's 33.
33. Yeah. Yeah. So it's smaller. Okay. So that is this issue. You don't. This can be used by the common sense, right? If you play the seesaw, okay. If you can balance this if you put if one person is over this side, right, and then this is kids, then if this is kid, the adult must be stay closer to the center, all right, and we can still keep it balanced. Do you agree?
Yes.
So that's it. That's simple as that. This is never.
Oh.
Is that simple?
Yes.
Yeah.
So, in the previous page,
yeah,
you've written tau 1 equals tau 2, so it's bad, but it doesn't because they're going different direction.
Well, the direction will be another good question, because the reason this direction will be how to rotate. Can you see? If you consider F2. The seesaw were attended go that direction. Do you agree?
Wait, will you say F2 is heavier? It's stronger.
Yeah. So each, say if you push, for example, if you go to this backside, if you push here, can we just assume that if you push this additional force here, right? And what would happen? The balance will be these seesaw were no longer balanced, right?
Yeah.
So the seesaw will move that in this direction. Can you see?
Yes.
In that direction, okay. So that is why this direction will determined that in this case push down, right? Push down.
Yeah.
So therefore, the force will that will determine which direction this seesaw will move, will rotate. It's called rotation. You see, rotation. Can you imagine that the seesaw is rotate about this axis?
Yes.
So this is you can imagine there is axis at here at this point. I use this color here. At this point, you can imagine there is an axis. The seesaw can rotate about this axis.
Yeah.
Okay. And probably I will take another example. Example 1, example 2. This time I will let's consider if, for example, if you have the how do we make an example here? Let's find an example for you. So if you, well, I think we will just focus on this example for time being, all right? And if you have any complicated question, example, I can discuss with you. Right?
Okay.
Today we just go quickly. And another topic is a spring. Okay, it's a spring. Spring is can be considered is when we study the spring, we normally don't consider the mass of spring. We just this is ideal. So this is just the spring without mass.
Yeah.
Without mass. This is ideal model without mass. Otherwise, the question became too complicated. For example, if we just consider the if you put the mass, if this is spring, okay, this is simplify the spring, okay, yeah. And without any mass, without any weight, they have original length. You see, so this length is original length. Can you call it air null? You see,
yeah,
okay. I just highlighted this spring, yes. However, if we put the weight here, what would happen? If I put the weight here, and the spring will be getting longer, right? Getting longer, elongated. Okay, so that is what when we put the object. So in this time, if I put the object here, weight here, can you call this mass m, right? So on the other hand, if we consider another spring which is horizontal, maybe I can draw another setup. So this time, we can also consider that a spring is fixed on the. Can we consider another spring which is horizontally placed? This is spring here,
yeah,
right? And so if this is original length, can we call the air null here, right? If, however, if make it longer this time, I can draw the two scenario here. So if we using the force, so this is has the object here. You can connect with object here. So one scenario is makes longer, can you see? Okay, of course, to do so, we have to use the force, right? We have to use the force. So to do so, we have used the force to make it happen, right? Or on the other hand, we can compress this spring, you see, make it shorter. So this is equilibrium. So this is called the balance positions, or sometimes called the equilibrium position.
Yeah.
So in both cases, the length changed. Can you see?
Yeah.
The length changed. In this case, we are obliged to use the force towards that direction. Can you see? To compress that.
Mm-hmm.
So this force, when we use a spring, can be described by a simple equation. It's called the Hooke's law. That is Hooke's law. Hooke studied this force before. So what he just used experiment to determine the dependence of this force, elastic force, as their displacement. Can we call this is a change? X L can you see X represents the change of their length? Can you see this is an absolute value? Yeah.
Yes.
So he did. So can you guess what would be the dependence of the force? If you make it longer, the force will increase. All right.
Yes.
And if you decrease, and also the force will increase, but the force's direction is different. So basically, after series experiment, he got this simple linear dependence if the change is not too big. Okay. So based on this experimental measurement, he argues that if the change of the length is not very small, not very large, then we can describe this dependence as a straight line, linear function, you see?
Yeah.
So how can we describe this formula? Do you want to try? If that is how do we use a mathematical equation to describe this straight line?
Equals.
It's a linear equation, right? It's a linear equation. So F should be equal to a constant, right?
Yeah.
Multiplied by K. That's it. That is Hooke's law.
Yes. Why is it negative? It says on the.
Sorry. Yeah, that's right. At the moment, we only consider amplitude. Can you see? At this moment, we only consider amplitude. But if you, because the force is a vector, right? Force is a vector, right? It's a vector. So vector has both amplitude and direction. In this diagram, we didn't consider direction. If we don't want to consider direction, can we draw this? Can we edit the x-axis here?
Mm-hmm.
And this time, if I choose x equal to 0, then that will equal to the length of the. If I choose this origin here, this is x-axis, right?
Yes.
So this is a balance condition. Can you see? It's called equilibrium. Okay, equilibrium. And in this case, force is opposite. Can you see?
Mm-hmm.
Force is in direction of is positive.
Yes.
Okay, this external force. What will be the elastic force? Can we use a different color? The elastic force should be opposite. Can you see?
Yeah.
Okay. And in this case, elastic force will be go that direction. Can you see?
Yes.
In other words, the elastic force is always opposite to the displacement.
Yes.
So that is a good question. So in this case,
Okay.
so can you say, so when in this case, delta x is larger than 0. Okay. And in this case, an elastic force is negative. Okay. Yeah. Is negative. And when x is a negative, okay.
Yeah.
and the force is positive. Good question. So
Okay.
if you really want to draw this diagram, the diagram should be, can we make this diagram more realistic? And if we want to consider the direction as well, so you are right. So if this is inelastic force, if this is x, the displacement, the change in the length, can you draw the diagram to describe both the direction as well as the magnitude?
Is it like a V?
Yeah, can you draw any graph? You can draw the straight line.
Yeah.
Oh, no, we cannot. It's good trial. But in this case, if x is positive, you say you predict f is positive.
Mm-hmm.
It's not right. See,
Okay.
if x is positive, how can we redraw that? Yes. How about if x equal to negative? If x is negative, is the force is positive or negative?
Positive.
Yes. So, that's right. Yes.
Straight line.
That's right. So that is how to use this diagram to work out the force dependence. All right. If you want to know the direction. So from this diagram, the Hooke's law got the negative sign. You see, equal to k negative x. Can you see that?
Yeah, I see it.
It makes sense. So at the beginning, we just know the amplitude. Okay, this amplitude. So this is just for amplitudes. For amplitude. Okay, that diagram gives you the direction. Okay, both amplitude and the direction is included. Okay. So that is Hooke's law. Okay, and by the way, this diagram is called the force displacement diagram. It's called the force, or sometimes called the distance. But you can call the distance as well, length, distance, or force displacement diagram. Okay, or force length. You can call the length diagram. It's graph. It's very useful.
Yeah.
Because if I ask you the question, if I have this, if we go to next page, if we have this diagram, and this case, so this is force, right? And that is x, and if I just use this second diagram, this is a force. This force, can you see that is a force? This Hooke's law. Hooke's law. And can we work out how much work has been done?
Work equals.
Yeah. So if we will ask you to
energy.
work equal to change of energy. Did you mention? Do you mean that?
Yes.
But by definition, this is one formula. Another formula is a definition. Work is equal to the force multiplied the displacement.
Oh.
And multiply the cosine theta. Do you know this formula?
No, I don't remember. Maybe I learned it.
Yeah.
Because it's from.
Okay. Yeah. I just probably perhaps we'll just talk about ordinary. We don't have to use this diagram. We can. Okay. I keep that diagram here. Can we just consider the simpler case? So can we just consider the other diagram? Okay. For example, in this case, the vertical is just the force, and the vertical is displacement. Can you see? Displacement can be called delta x. Okay. And if we just consider a simple case, say this is a mechanics. If we put the box here, this is a box here, right? And if you apply the force this time, which is not necessary in the same direction, of the displacement. So this is force acting on the mass center, right? And you keep use this force. So this is called force. It's called F's force, and which is constant. And this axis, this is the x-axis, all right? So you make this object move towards that direction. So we needed to know if this is delta x, right? Delta x here. The work done. So how can we work out work done? So work done by the force F, all right? By definition, work is equal to the dot product of the force. Okay, do you remember the dot product and the displacement, delta x? Perhaps we just write the formula for you. In this case, this work should be equal to F multiply displacement and multiply the cosine theta, which is this theta.
Yes.
Can you see there are two directions? So that is the idea of the dot product. Can you see? Can we just draw one more diagram? So if you have in general, if you have two vectors, so this is A and that is a B, right? If you in general, if you have two vectors, and the angle between them is denoted as theta, right? If you have two vectors A and B, then the dot product, but this is the mathematical part, right? This is just math. The dot product of two vectors, by definition, A dot product B can be written as the magnitude A multiply magnitude B multiply cosine theta, right? Yeah. Can you see the similarity between these two?
Yes.
Yes, so that's how we use a vector dot product in mechanics. So in this case, so if the force is constant, then the diagram, the force is constant. This is just the horizontal line, right? So if we want to calculate the work done here, for example, this delta x, all right? So in this case, in this case, of course, this is a general notation. We have considered cosine theta, right? We have considered cosine theta. Perhaps I will go to something simpler. This time, we just consider a scenario because you haven't started. You have not started work, right?
Pardon?
You haven't. I just drew another. We just draw a simpler example. So this F. This time I make theta equal to 0, right?
Yes.
I make theta equal to 0, so that in this simpler case, if this object is moved by this force by delta x, all right? So we just consider simpler case. And by definition, the work done is simply equal to F multiply, this is a force,
yes,
multiply delta x. Because in this case, theta is equal to 0.
Yeah.
Okay. So what is cosine theta 0? What is cosine 0? 1.
1.
Yep. Can you see? So if I use this simple diagram of this example, and we can you see this is a simple example, the definition of work, okay, in which the theta is equal to 0. And then the work done will be exactly equal to this area. Can you see that?
Yes.
Can you see that? So that is the graphical meaning of this force displacement diagram. And similarly, if I just ask you, if I make if I just return to the Hooke's law, all right?
Yes.
So if I just, for example, this is original. This is spring. You see, this is original length, and then we make it longer. Can you see?
Yeah.
Okay, so that is a change in the length. So I will ask, of course, we have used force to do so, right? And when we do this, this force, we just keep its balance every time. The force will equal to the elastic force of the spring, right? So this red color force is represent external force, all right? And obviously, they have elastic force, which is opposite to this external force. Oh, at the beginning, there's no force, sorry. At the beginning, zero. At the beginning, there's a zero. Let's just redo that. There's no force here. So at the beginning, force is equal to zero. Okay, I just ask you a question. Do you know how much work has been done when we make this spring longer from original length to the extend? This can call this L no. This is L.
Yeah.
Can you work out how much work has been done? Based on this idea, so this area will represent the work done if the
it's just force times the length.
No, in this case, you have to consider in this case, this will be the area here.
Yeah.
That would be this area. Can you see the triangle?
So it's F times X divided by 2.
And a half.
Yeah.
Yes, that's right. Can you see that? So, so just by comparison, we can argue that in this case, the work done can also be raised. The work done can also equal to as a half of this rectangle, right?
Yes.
That's equal to the force. This is force kx, right? And also multiply this distance is also for the force. Can you see?
Yeah.
So therefore, that will equal to half k x squared. So this is the second formula. And this work done according to this, according to the first formula about the work done will equal to change in the energy, right?
Yes.
This time, the energy is called the potential energy, not elastic, because we move this very slowly, right? So that is the second. This is the second formula for the spring. That is work done by the external force and work done by elastic force can be written as this form. So therefore, we can write a new formula for this spring, which is from this formula, we can argue that the potential energy, because originally, if I write down here, so the work done is half k x squared, okay, should be equal to the change in the potential energy. So that is a potential energy. And can we just consider the potential energy at zero is zero? Let's just initial potential energy is zero.
Yes. Yeah.
So therefore, from this one, we got a new formula. That is the potential energy of the spring is equal to half kx squared. Okay, these two formula. We can use this for two formula to solve not our problem.
Yes.
So this is called the potential energy. Can write down here. It's called potential energy of the spring. So this is a potential energy stored in a spring.
Yeah.
Okay.
I got the math part, but just conceptually, so this is like a spring.
Yeah.
The right side is F, and the left side is the elastic
force. Yes.
Yeah. So when the spring is stretches,
yeah.
is it when it stops moving, is the force balanced?
Oh, it's not balanced. You have to keep the force, external force. Good question. So
Yeah.
if I return to the first diagram here, so if without okay, this is new balance at this moment is still balanced because let's consider this. Can we consider this case first? All right.
Yeah.
If we remove this force, what would happen?
Bounce
Release.
back.
It just spun back. Okay.
Yeah.
And so this object, so that's a good question. So this object will move towards the opposite direction, right? Negative.
Yes.
But will it stop right away at the equilibrium position?
It goes over.
You will continue move because at that time they have gained the kinetic energy, right?
Yes.
So the kinetic energy will reach the maximum. You see. And so you'll keep moving. I should show you some. Oh, I got example here.
Oh.
I got. Can you see? This is a good example. Can you see?
Mm-hmm.
Can you see that?
Yes.
Okay.
Wow.
So basically, if you wait for it to balance, reach, all right, and if you use external force, push it down, and the release, and it will oscillate. Can you see?
Yeah.
Okay. So similarly, if you have reached the balance condition, if you put it upward and let it go, it also will balance. It also will evaporate. Can you see?
Yes.
So that is so the spring mass on spring is a good example to study the vibration. When we study the wave, have you studied wave in physics?
Yes.
Yes, you know that the wave is is made by many local vibration. Okay.
Yes.
So that is why let's just return to this diagram.
Yeah, I was saying that when you stretch it out and you stop moving, stop applying force.
Yeah.
But just holding it there is the elastic force and the applied force even.
You can adjust this external force to make it balanced.
Yes.
But if you release the force, and the object will oscillate. Does that make sense?
Yes. I'm just not quite understand the elastic force.
Elastic force is such the force is always follow the Hooke's law. Can you see? If I return to this diagram, the first diagram, so if this x is not too big, right? So therefore, you can predict the elastic force by using this diagram or using this Hooke's law.
Yes.
Can I put some number here? For example, this is for example, this is 0.5, okay, and this is 0.25, right? So if you know this number, and this k is constant, okay, it's called elastic constant.
Yes.
Elastic constant. So if you know this one, then we can calculate the force here. Can you see?
Yes.
So this is a formula. Hooke's law is a formula for elastic force.
Yeah. Oh, okay. I thought it was
sense?
the formula for the applied force.
Not applied force. We use this force to just make this happen. You see, the spring cannot automatically get longer, right?
Yes.
You have to use the force to change. You have to use the force. Can you see? You can either use force. So this is a balanced condition, right? At this moment, by the way, in this case, what is elastic force? In this case, what is the force? What is elastic? Zero. That's right. And in all other cases, we just assume that elastic force equal to external force.
Okay. Yeah, I got it. That's what I'm asking.
Yeah. Okay. And can we just return to your note to see if any other missing we didn't discuss today?
I think that's all, but I'm still a bit confused about levers.
We can return to lever. about a point on the object. They have different, they also talk moment of force, but it's the same as a torque, okay? Momentum of force and the torque we used today is the same.
Okay.
Can you see the moment of force?
Yeah.
Yeah. It's just different name. For example, can we just talk?
What does it mean? Taking moments.
The moment is the same. I just show you. This is first moment. Can you see this? Can we just go to the whiteboard? And let's go to Nevner. Okay, so we use the torque here, right? We call it torque. It's also the torque momentum of force. So this is this is just different, same thing, different name.
Yes.
It's called momentum. Momentum.
Oh, it's related to momentum.
Yeah, of force. Yeah. So they use, sometimes they use mathematical name because any moment can be considered as for example, by definition, momentum, this is not mass, this moment can be written as they have different order. Can you see? This is in here, multiply something. In our case, is a distance, right?
Yes. But it's a momentum.
Just probably just simply say you from now on we can either use a torque or momentum to describe this quantity.
Okay.
The tau. Okay.
That's the same thing.
Okay. Yeah. And momentum never. That is how these are related to some simple machine. Because I read that in this type of test, you are going to understand how the simple machine work, right?
Okay.
And another thing is, have you studied the pony system? Pony system. So that's you have, for example, you put the this is one single wheel, single pony. So this one you can, in this way, you just they just change the direction of force. All right, they change the direction of force. It's fixed. It's fixed. And another thing is moving. See, another is moving. You see. So that another pony system is like this. Okay. So in this way, you can in this way, the force. So this weight, can you see this weight? This T is tension here. In this case, these two forces are equal, right?
Yeah.
The T1 equal to T2, all right? Now in this case, the tension inside can equal the T1, T2. Do you know the relation between the T1, T2? This is T1.
They're both T1.
Oh, sorry, T2.
Yeah.
Yeah, T2.
No.
This is halved, can you see? So in this case, because if you use this wheel, which is movable, then the relation will be so T1 will be T2 will be equal to half of T1. So you can save some force. Okay, you don't use that. If object is very heavy, then by using this moving pony, then you should be able to use half of the force of the weight.
Yeah.
And by the way, this also you can consider this also the balance of the level. Can you see? If I just draw this, this is for example, you can if you consider this a simple setup here. Okay, if you put a different weight here, you see.
Yes.
And then you will decide which direction this wheel will move.
So the heavy.
Can we call this M1? This capital M. Okay. So M is larger than N. So which direction? Just common sense. Which direction this wheel will rotate?
M to the larger M side.
Yeah, that will rotate this direction. Can you see?
Yes.
And these phenomena can be explained by our levels. Okay, can you see?
Yeah.
So if do you remember the two R here? Can you see? These R, there's another R. Can you see? So in this case, the two R is the same. Is a radius.
Yes.
Okay? But the torque is different. Okay. So for the torque, this torque, one torque is torque 1 is equal to R multiply M G.
Yes.
Okay. Torque 2 is equal to R multiply small mg. So therefore, in this case, you can that's why the wheel will rotate that way. Or in other words, this object will fall and this object will go up.
Okay.
So that can be, in this case, R1 is less than, or is if I use R notation, is larger than R2. Can you see?
Yes.
Because they are not equal. So in this case, they are equal. Can you see? So tau 1 is equal to tau 2.
Yeah.
Yeah, perhaps we can stop here today. All right.
I got it.
Okay,
It's much clearer.
Okay.
Yeah.
I will send this to you. Okay. I will send this thing to you. Okay. See you Saturday. Okay.
Thank you very much. See you.
Okay. Goodbye.
Goodbye.
I will stop sharing.